there is a theorem. So last time we already talked about it. So basically linear map since a basis to a basis is isomorphism. We're going to do a good proof. So there's a transformation from the vector space V to vector space W is a linear transformation. And let V1 through Vn be basis for the vector space V. And W1 through Wn be the basis for W. Okay, our theorem is if we have a transformation, if T of Vk equals Wk for all k is basically from 1 to n, then we say T is an isomorphism. Okay. So prove this. So basically for this linear transformation, we already know the transformation on the basis. So we know that if we have a transformation on the basis, then basically we know the whole transformation in the space. So all we need to do is we need to define the map. So we need to define the map that can be the inverse of this transformation we have. So again, to define a transformation, we can only define on the basis. So let's define the inverse transformation, where the inverse of T maps W1 to V1. And W2 to V2 all the way to Wn to Vn. Right, now we have this transformation. We can then verify if it's an isomorphism. Again, isomorphism is invertible, and for invertible, we just need to compose the transformation and see if it's the identity transformation.
Yeah.
Right. So let's do T inverse. Compose with T first. inverse T. And for any V, we should be able to write V as a linear combination of the bases. So
Yeah.
B of 1 V1 plus of 2 V2 plus all the way to of NVN. And then since T is a linear transformation, we can rewrite wherever inside to be alpha 1 TV1 plus alpha 2 TV2. Okay. Now we know that TV1 equals W1. So all right, now's the time for the T inverse. So T inverse is also linear transformation. We can basically distribute this transformation inside to be alpha 1 T inverse W1 plus alpha 2 T inverse W2. All right, and based on our definition of the T inverse, we'll get back to alpha 1 B plus all the way to alpha n Vn. And this is just V. All right, now we have a transformation of V. We get back to this V. So basically, having it back to the original V, it means that it went through a original transformation. So the identity transformation. All right, now we've proved that the composition of these two transformations is basically the identity transformation. And then we can just do another T composite with the inverse FW. Wait, oh, and after that we will get back to this W, and that's okay. So after verifying these two, we'll have the conclusion to say T is invertible. Okay, so we actually have a corollary from here.
Is a corollary just like a thing you conclude from another thing?
Yeah, kind of. Yeah, there's a lot of like theorem, proposition, corollary. I don't really know the difference between them.
Okay.
Okay, so corollary says if we have a m by n matrix, oh, wait. if this matrix is invertible, then we know that. So a matrix is invertible if and only if its columns form a basis for Rn. So this one we can think of if we have a matrix A. So if we let A multiply any standard basis of Rn. So if we think of A multiplied by E1, then basically this matrix A is has one column right here, say V1. Okay, let's say that this is like the first column is A1, the second column is A2, like that. Do you see my cat? Can you hear my cat?
No.
Oh, okay, great. Okay, I have a matrix look like this. And if I multiply by E1, then basically what I get is just A1 is multiplying this E1. Because E1 is like 1, 0, 0, 0.
Mm-hmm.
So basically all the columns can be multiplying different EK. So each column can be like, this can be, think of it is A1 multiplied by E1, and this is like
Because isn't that just
A2 multiplied by E2.
because AE1 is just the first row, right?
Yes. Wait. It's the first column.
So what? AE1.
Right. Because so basically, when we do multiplication, we use the first row to multiply by the first column, but all these are zeros. And then we use the second row to multiply by same thing, the second, right, to get the second entry. So basically, A1, A times E1, we'll just get A1.
Mm-hmm.
So basically each column can be think of like we're doing a transformation on the standard basis. And then if it's invertible, we are if we are doing a transformation of basis, then it is invertible or it's isomorphic if we talk about the transformation. So this is basically our reverse direction of this corollary. First direction, invertible to prove the basis. We need to prove its like span Rm and linear independent. Yeah. And for the first direction, invertible to prove the basis, we need to prove its like span Rm and linear independent. Yeah. So we just need to find the basis and then a linear transformation maps from one space to another space, and it actually maps to the other bases, and then we can say the columns from subbases, because the columns are just the bases after the transformation. Okay, so and then we can talk about the polynomial space we had some encounter with. So if I have a polynomial, if we have a polynomial PNR, we say it is isomorphic to the Rn+1 space. Okay, the basis of PNR is 1 t or x t squared all the way to tn. And for R, we can use the standard basis E1, E2 through En. Okay, again, to prove these two are isomorphic from the theorem, we only need to find a transformation that we say this transformation of 1 will be mapped to E1, and transformation of T maps to E2. The way to transformation of T to the nth power maps to En+1. All right, as long as we define a transformation like this, then we can say these two vector space are isomorphic.
Okay.
So for example, we can say, I think we have this example last time. We can say P2R. And one example in P2R can be 3t squared plus 6t minus 4. Okay, if we want to say P2R is isomorphic to R cubed, then we should be able to represent this thing in R cubed. And last time we say we can do to 4, 6, 3 for R cubed, because we mapped the 1 to E1
Yeah.
to T to E2 and T squared to E3. Okay, now we finished the invertible part. We can move on to introduce subspaces. So a subspace is a non-empty subset, and it should be closed under the operation. Closed under addition and scalar multiplication. So basically, if we have a vector inside of X, then after multiplying a scalar, it should be also inside of X. And same thing for the addition. So it means that if both V inside of X, then V plus W should be inside. So same thing, if V inside of X, then a scalar multiplied by V should be inside. Right, and this non-empty subset, we know that scalars scalar basically include 0. So for this subset, we at least 0 is inside the 0 vector.
Mm.
And we say a subspace X with operations inherited from V, we call it it's also a vector space.
By operations inherited, like what do you mean? You mean just addition and scalar multiplication?
Yes. So basically, if we define the same, if we define the same addition and scalar multiplication as V, where V is where the X come from, then it's also a vector space. So one example of subspace is the set of only 0. 0 inside of V is a subspace. Okay, to check if it's subspace, we check if it's non-empty and if it's closed. So first, this is non-empty because 0 is inside. All right, and second, we check the additive closeness. So 0 Again, in this subset, there's only one zero vector. So all we can check is 0 plus 0. It's 0. It's also inside of the space.
Mhm.
So same thing for the scalar multiplication. Any alpha times 0 is also 0. And that's inside of the space, this subset. So one other example can be the vector space V itself. So anything itself is a subset of itself. So if we have a set, then itself is also a subset of itself. So V is also inside of V, and it's a subspace.
Mm.
Actually, we can think of other examples. So if we think this V as, for example, R squared, or just R, then we know all the integers belongs to this R, and all the integers is also closed under the addition scalar multiplication if we just use integer scalars. And we can say this integer z is also a subspace. Now let's define the kernel. So say we have a transformation from V to W, and we say it's a linear transformation. The kernel of T. Sometimes we call it null space. Is defined to be kernel of T is all the vectors belongs to V such that after the mapping, it maps to 0. So if we look at the graph, let's say I have a vector space V, I have a vector space W, and I have a transformation T that do the mapping. So there are a lot of mappings, and for example, this vector V1 is mapped to this W1, and we have some of the vector, say V2, mapped to the zeroth vector. And then we say this V2 is one of the elements in the kernel of T. Maybe there are not there are more than one vectors, say V3 also maps from this vector space V to 0 in the W space in the transformation with the transformation T. So in this case, both V2 and V3 belongs to the kernel of T. So same thing, to determine if it's subspace, we check the non-empty and the closeness. So non-empty as so we at least know the zero vector in V belongs to the kernel of T. Because for any linear transformation, we would just map zeroth vector to the zeroth vector. So for any V, I have a say this V1 and V2 in R2. And one transformation could be like 2V1 plus or minus V2 like this. V1, V2 both be 0 is the zeroth vector. And V1 be 2 and V2 be, I mean, V2 be 2 and V1 be negative 1 is another null space. And this is a transformation from R2 to R. And then for the closeness, if we have V1 and V2 inside of the kernel, then basically we're saying that TV1 is 0 and TV2 is 0. And we know that 0 plus 0, if it's a linear transformation, it equals V1 plus V2. And 0 equals that, so 0 has to be equals to, if we add V1 and V2 together first. So, V1 plus V2 is also inside of the kernel. And now we have another definition. So we already know the kernel. There's another set, we call it the image of T. So for a linear transformation, again from V to W, or you might already seen it with the name range.
Oh, okay.
Yeah, the range of T or the image of T is defined to be image of T is all the vectors in W where there exists a vector V that after the transformation it becomes W.
Yeah.
Okay, so one example could be a mm, so if I have a V and W, all right, all the mapping from V1 to W1 are these. So some of them are zeros, right? So there are only 5 elements in V and there are 4 elements in W. So in this case, range of my range in W are, well, there might be another element in W, but since this W5 is not hit um by anything after the transformation, then this range of W consists only uh W1 through W4.
Mm-hmm.
So we only count the elements inside of the range if it's hit by this transformation. Okay, another proposition is that this range of W or image of W, I mean, the image of the transformation T is a subspace for W. Okay, these are just some introductions on the kernel range and basically the definition of subspace. We can move on to the chapter 2, where we calculate the matrix. So same thing, we start from a definition. So we say an equation is a linear uh, if the exponent on all x's is smaller than or equal to 1. Okay, now a system of equations. Is a set of equations to be solved simultaneously.
Mm-hmm.
So for example, in R2, if we have 2x1 plus x2 equals 8. and x1 minus x2 equals 1. So this is a system of equations with two equations and two unknowns. And they're not linearly dependent, so we can solve it. And we can just like add these two together, and we can basically arrive 3x1 equals 9, x equals 3, x1 equals 3. And we know we can solve for x2 where x2 equals 2. So basically we have two unknowns and we solved for these two. And now for linear algebra, instead of using the representation of equations, we use matrix to represent the system. So we want to solve for x1 and x2. All right, the first one. So for matrix multiplication, we know it's like row times column. So the first entry is associated with x1 is 2, and the second entry is associated with x2, which is 1. So same thing for the second row, x1, the scalar of x1 is 1, the scalar of x2 is -1.
Mhm.
So what we're actually solving is this matrix multiplication. We want the result to be a vector of h1.
Mhm.
So this is an equation with two unknowns, but we can have like many unknowns. For example, if we have equations such as a11 x1 plus a12 x2 plus all the way to a1n x n, and we know that equals b1, and we have a21 x1 plus a22 x2 equals b2, all the way to an1 x1 add to an xn plus bn. Then we can write it as the matrix a11, a12, all the way to a1. So a21 all the way to an1. Wait, let's use m for this. So we'll have a matrix with m rows and n columns. All right, this is a matrix multiplied by our unknowns. That's x1 through xn. It'll be equal to b1 through bn. And we call this first matrix the matrix big A. The unknowns to be the vector of x equals the vector of b. So any system of linear equations can be written as a matrix equation, matrix product equation. And sometimes we write this as a augmented matrix. See here. So we ignore the unknowns. We just write the matrix A on the left side and the B vector on the right side. Right, and now we have everything that we need to solve for the x's.
So like what we wrote on the top,
Hmm?
like the first thing we wrote.
The first row?
Oh, I see. Never mind.
Oh, okay. All right, so to solve for this augmented matrix, we use row operations. So let's first define elementary row operations. So there are three operations. The first one is called row exchange. The second one is called scaling. The third one is row replacement. So row replacement means we replace row I with alpha row I or row I plus alpha I row J. Well, it's the same thing. Alpha cannot be zero. So row exchange means we change the order of row I and row J. And scaling means we multiply row I by alpha. So we believe that these three row operations does not change our solution. And we basically to solve for the linear system, we want to use these row operations to bring the augmented matrix to a form called the echelon form or the reduced row echelon form. But let's do an example of how to solve it with these first. So use our augmented matrix. We have we have a row 1 of 2, 1 and row 2 of 1 next to 1. And that is corresponds to the original equation to x1 plus x2 equals 8. X1 minus x2 equals 1. Okay, first we can do a row exchange. So let's say we want R1 and R2 to be exchanged. So our first line would be 1 next to 1, 1. Our second row would be 2, 1, 8. And our equation does not change. We just change the order.
Mhm.
Mm.
But what's the point with swapping? Isn't it just like doesn't really do anything?
So in terms of solving, it doesn't do anything. But after reaching the end, it will be written in a better like way to see. Oh, I'll show you in the end. So basically we do the exchange right now, but we can also like not do the exchange right now, but like in the end, if we want to organize better, then we do the exchange. So, and then to solve it, we can okay, then I'll get 3x2 equals 6. Okay, and now we divide the second row by 3, we'll get the x2. Mm, Now, after we have the um our x2, we can use x1 and we can add row 1 and row 2 to solve for x1. So two after addition we have x1 equals 3. Okay. So then this row exchange is not necessary. And what we did is, so we've seen row exchange, we've seen the scalars, and we've seen the row replacement. And after these 3 row operations, we've ended with the x1 and x2. Okay. Now so uh in the end, like sometimes we cannot solve for the x and y's, and if we do or if we do not, we always want to write in this form, like the first one is on the first entry, the second one is on the second entry, like that, and we call it the echelon form. and and in this case, this is the reduced echelon form. So
So it's like when oh, is it like kind of like the identity?
yeah, kind of, but it's basically in equation we want to write x1 equals first, x2 equals second. Yeah, just keep them in order. So definition. So a matrix is in echelon form if so all rows with entries are zero are below all non-zero rows. So if we have a row that's all of the entries are zero, then it should be on the way bottom. Non-zero rows. And then the order for non-zero rows. We say the leading entry should be strictly to the right of the leading entry of the previous row. So for the echelon form, it could be a matrix look like 2, 0, 1, 1, 2, 3. And whatever this augmented column to be. Okay, and now let's define the reduced echelon form. Or reduced row echelon form. Uh, okay, so first it's also in echelon form.
Mm-hmm.
And then we also want all the pivot entries to be 1. Pivot. And all entries above pivots are 0. So one example can be what we have right here. Another example can be, so if we have a lot of equations with not as many unknowns, we would get, for example, 101, 10 pivot entries. Okay, we might end up with a augmented matrix look like this. So if it's in this case, then it means that we don't have the unique solution we want.
Mm-hmm.
Or it could be, so even things like this is also a reduced row echelon form because we do not have the pivot entry for the third unknown. So one example, let's just do an example and it would be the end of today. So if I have equation, a system of equations, so the first equation is y minus 2z equals 3. The second is x plus y minus 3z equals 7. Third is x plus 3y minus 7z equals 13. Okay, our first step would be to rewrite this equation to a augmented matrix. Okay. The first line would be no x, 1y, negative 2z's equals 3. The second is 1x, 1y, negative 3z's equals 7. And 1x, 3y, negative 7z's equals 13. Okay, so first, as we want the first entry to be a pivot. So instead of having 0, we need to exchange for some row with a 1 to the top. So our first operation can be row 1 exchange with row 2.
Mm-hmm.
Okay, now it would be 1, 1, negative 3, 0, 1, 2, 1, 3, 7. All right, now here I don't want this one here, but I can use my first row to get rid of this 1 on the 3, 1 place. So I want to replace the third line with R3, subtract R1. So first 2 lines doesn't change. The third line would be 1 minus 1, 0, 3 minus 1, 2, and I have up to 4. Right. And here it becomes a 0. And we can further reduce the second entry on R3. So let's do R3, subtract twice of R2. So I'll end up, so first line does not change again. Right. So the third line, subtract twice of R2 will be 0, 0, 0. All right. Now we're in the echelon form. All right, to get to the reduced echelon form, the only thing we don't want is, so all my pivot entries are 1 now, but I want all entries above pivots are 0. So this one should be 0. Okay, we need to do one more step. For example, we can use R2 minus R1. The first line doesn't change. 1, oh, sure. R1 minus R2 because we want to replace R1. But so second and third line doesn't change. 0, 1, 2, 0, 0, 0. Now I have 1 minus 0, 1 minus 1, negative 3 minus negative 2, to 1. Okay, now these 3 columns are corresponds to x, y, and z. So x and y are now the pivots variables. I have 1, 1 here. But z, z is a column with no pivot. So we call it a free variable.
Oh.
And we can only solve for the pivot variables in terms of the free variables. So that means so we can further translate the first equation to be x minus c equals 4 and y plus 2z equals 3. So we cannot solve for them, but we know their relationship. Basically, z can be anything, but x should be 4 plus z, and y should be 3 minus 2z. Or you can write it as a vector. So this vector xyz can be written as 430 plus a z multiplied by so z can be z, and z should be 3 minus 2z, so it's -2 here. Hmm? And okay, z 4 plus z, so it'd be 1 here.
I see.